welcome to this problem walkthrough. In this session, we'll explore an interesting problem from LeetCode, problem number 1734, Decode XORed Permutation. We'll break down the problem, analyze different approaches, and understand how to tackle it step by step. Let's get started. In this problem, you are given an integer array called encoded, which is of length n1. This array is derived from a permutation of the first n positive integers. A permutation is essentially an arrangement of all integers from 1 to n in some order, where each integer appears exactly once. Now, the encoded array is constructed by XORing adjacent elements in this permutation. Specifically, for every index I from 0 to n2, the value at encoded, I, is the result of XORing perm, I, and perm, I plus 1. Your goal in this problem is to reverse this process, to decode the encoded array and determine the original permutation perm. The input will be the encoded array, and the output should be the perm array with a length of n. Let's look at an example to better understand the problem. Suppose the input is encoded equals 3, 1. This means the original permutation was XORed element by element to form this array. The output for this example is perm equals 1, 2, 3. Why? Because when we XOR adjacent elements in this permutation, 1 XOR 2 gives 3, and 2 XOR 3 gives 1, which matches the encoded array, 3, 1. Therefore, the original permutation that satisfies this encoding process is 1, 2, 3. Now let's consider another example. Suppose the input is encoded equals 6, 5, 4, 6. The output, in this case, is perm equals 2, 4, 1, 5, 3. Here's how it works. If we take this permutation and XOR adjacent elements, 2 XOR 4 gives 6, 4 XOR 1 gives 5, 1 XOR 5 gives 4, and 5 XOR 3 gives 6. These XOR results match the encoded array, 6, 5, 4, 6. This demonstrates how the permutation, 2, 4, 1, 5, 3, is the original sequence that was encoded. The problem also comes with specific constraints and edge cases to consider. First, the length of the permutation can range from 3 to 100,000. This means you need an efficient solution that can handle very large inputs. The encoded array will always have a length of n1, and each element in it will be an integer between 1 and 1000000. For edge cases, think about scenarios like when encoded has only one element, which corresponds to the smallest possible input. Also, consider very large inputs where the array length approaches its upper limit. Another interesting edge case is when all values in the encoded array are identical, such as 5, 5, 5, 5. Finally, the permutation might start or end with the largest possible value, like n or 1. These edge cases and constraints will be critical in designing a robust solution. To start, let's consider the brute force approach. The intuition here is straightforward: generate all possible permutations of the first n positive integers and check which one matches the given encoded array. For each permutation, we calculate the XOR of adjacent elements and compare it to the encoded array. If there's a match, we have our solution. However, the complexity of this approach makes it impractical. Generating all permutations requires factorial time, O, n, and verifying each permutation against the encoded array adds an additional O, n, per permutation. This results in an overall complexity of O, n. Asterisk n, which becomes computationally infeasible as n grows larger. Therefore, this approach is unsuitable for larger inputs. Now, moving to the optimized approach, we can leverage the mathematical properties of XOR to solve this problem more efficiently. One key observation is that the XOR of all numbers from 1 to n, what we can call the total XOR, can be computed directly. This provides the XOR of all elements in the original permutation. Additionally, the encoded array itself represents the XOR of adjacent elements in the permutation, allowing us to work backward to reconstruct the original sequence step by step. Using these properties, we can deduce the first element of the permutation and reconstruct the entire array. Here's how. First, we compute the total XOR, which is the XOR of all numbers from 1 to n. Then, we compute odd XOR, which is the XOR of all odd indexed elements in the encoded array. By combining these, we can deduce the first element of the permutation using the formula perm 0 equals total underscore XOR caret odd underscore XOR. Once we have the first element, the rest of the permutation can be reconstructed iteratively. Each subsequent element is derived using the relationship perm I plus 1 equals encoded I caret perm I. This step-by-step reconstruction ensures that we efficiently decode the permutation without needing to generate all possibilities. In terms of complexity, computing total underscore XOR and odd underscore XOR each takes O, n, and reconstructing the permutation also takes O, n. Thus, the overall time complexity of this approach is O, n, making it highly efficient. The optimized XOR-based method is a clear improvement over the brute force approach. Ultimately, the XOR-based approach is the chosen strategy due to its efficiency and mathematical elegance. The core idea is that XOR allows us to deduce the permutation elements without explicitly generating all permutations, avoiding the exponential time complexity of the brute force method. Additionally, the space complexity is O, n, as we only need to store the decoded permutation array. While this approach does rely on understanding the properties of XOR, which may be less intuitive for some, its performance and scalability make it the best choice. In conclusion, by leveraging XOR properties, we achieve an O, n, solution for decoding the permutation, making this approach suitable even for larger inputs. This combination of efficiency and practicality highlights why the XOR-based method is the optimal strategy for solving this problem. To solve this problem, we start by understanding the XOR operation, which is key to decoding the permutation array. XOR, or exclusive OR, has unique properties, a XOR A equals 0 and a XOR 0 equals A. Additionally, XOR is both commutative and associative, meaning the order of operations doesn't affect the result. These properties are crucial because the encoded array is defined such that each element is the XOR of two adjacent elements in the permutation array. Specifically, encoded, I equals permutation, I, XOR permutation, I plus 1. This means, if we know one of the values in the XOR operation, we can deduce the other. Another helpful insight is that the XOR of all integers from 1 to n, which we call total underscore XOR, can be pre-computed. This value will play a central role in determining the first element of the permutation array. To compute total underscore XOR, we simply iterate through the numbers 1 to n and XOR them together. For example, in Python, this can be achieved with a simple loop where total underscore XOR caret equals I is executed for each value of I from 1 to n. Once we have total underscore XOR, we can move on to leveraging the encoded array to compute the XOR of specific elements in the permutation array. The goal here is to isolate the first element of the permutation. To do this, we calculate the XOR of all odd-indexed elements in the encoded array. Why odd indices? Because the encoded array represents the XOR of consecutive elements in the permutation array, and by isolating the odd indices, we effectively extract the XOR of all odd-positioned elements in the permutation array, excluding the very first element. This calculation is straightforward. Initialize a variable odd underscore XOR to 0, and for every odd index in the encoded array, XOR the value at that index with odd underscore XOR. The result of this operation is the XOR of permutation 1, permutation 3, and so on. With odd underscore XOR calculated, we can now use it alongside total underscore XOR to determine the first element of the permutation array. The formula is simple. Permutation 0 equals total underscores or XOR odd underscore XOR. This works because total underscore XOR represents the XOR of all elements in the permutation, and when combined with odd underscore XOR, the odd indexed elements cancel out, leaving only the first element. After determining the first element of the permutation array, we can reconstruct the entire array iteratively. The formula we use is based on the relationship between the encoded and permutation arrays. Encoded, I, equals permutation, I, XOR permutation, I plus 1. Rearranging this equation gives us permutation, I plus 1, equals encoded, I, XOR permutation, I. Starting with the first element, which we've already calculated, we can use this formula to compute each subsequent element in the permutation array. For example, the second element can be found by XORing the first element with the first value in the encoded array. Similarly, the third element is found by XORing the second element with the second value in the encoded array, and so on. This process continues iteratively until all n elements of the permutation array are reconstructed. The key insights here are the simplicity of XOR operations and the iterative nature of the reconstruction. By isolating the first element and leveraging the relationship between adjacent elements, we avoid the need for more complex operations like division or subtraction. Instead, the algorithm builds the solution step by step, directly from the given encoded array. To implement this algorithm efficiently, we rely on a few key data structures and variables. The encoded array stores the XOR of adjacent elements, and the permutation array is used to store the reconstructed sequence. Additionally, we use variables like total_XOR and odd_XOR to facilitate quick pre-computations. In terms of complexity, the algorithm is highly efficient. The time complexity is O(n), as we perform three main operations: computing total_XOR in O(n), calculating odd_XOR in O(n/2), and reconstructing the permutation array in O(n). Together, these steps result in linear time complexity. The space complexity is also O(n), as the permutation array requires space proportional to the size of the input, while other variables like total_XOR and odd_XOR require only constant space. Finally, we must handle edge cases. For instance, if the input size is small, such as n equals 2, the algorithm should still function correctly. We should also validate that the encoded array size matches n1 to avoid errors. Additionally, the implementation should scale efficiently for large inputs, ensuring it can handle n up to 100,000 without performance degradation. Let's walk through an example to solidify these concepts. Suppose the encoded array is 3, 1, and n is 3. First, we compute total_XOR for the numbers 1 through 3. XORing these values gives 1 XOR 2 XOR 3 equals 0. Next, we calculate odd_XOR by XORing the odd-indexed elements of the encoded array. Here, encoded 1 equals 1, so odd_XOR equals 1. Now, we find the first element of the permutation array using the formula permutation, 0 equals total_XOR odd_XOR. Substituting the values, we get 0 XOR 1 equals 1. With the first element determined, we can reconstruct the remaining elements. The second element is calculated as permutation, 1 equals encoded, 0 XOR permutation, 0 equals 3 XOR 1 equals 2. Similarly, the third element is found as permutation, 2 equals encoded, 1 XOR permutation, 1 equals 1 XOR 2 equals 3. Thus, the reconstructed permutation array is 1, 2, 3. This example demonstrates the step-by-step execution of the algorithm and highlights how each part of the computation leads to the final result. To solve LeetCode problem number 1734, Decode XORed Permutation, we need to reconstruct the original permutation array from the given encoded array using XOR properties. ###explanation. 1. Input analysis. The input encoded array has n1 elements, where each element is the XOR of two adjacent elements in the original permutation array. Our task is to find the original permutation of size n. 2. Step 1. Compute XOR of all numbers in 1, n. The range of numbers in the permutation is 1, n. The XOR of all these numbers, total_XOR, is computed using a loop. This helps us later in deducing the first number of the permutation. 3. Step 2. XOR of odd indices in encoded. To calculate the first number in the permutation, we need the XOR of all numbers at odd indices in the encoded array, odd_encoded_XOR. Using XOR's associative property, the odd indices in encoded indirectly correspond to all elements of the permutation except the first one. 4. Step 3. Calculate the first number. The first number in the permutation is derived as first equals total_XOR caret odd_encoded_XOR. This works because XORing all elements cancels the intermediate ones, leaving only the first element. 5. Step 4. Reconstruct the entire permutation. Using the first number in the encoded array, we can iteratively compute the remaining permutation. Each next number is obtained by XORing the previous number with the current element in the encoded array. 6. Edge cases. The algorithm handles cases where the permutation size is small, e.g., n equals 2. Since XOR is commutative and associative, it guarantees correctness regardless of the permutation order. Finally, the reconstructed permutation array is returned as the result. The algorithm runs in O(n) time, which is efficient for the problem constraints. Here, we start by defining a class called solution and implementing the decode method, which takes an array called encoded as input. The goal of this method is to decode the XORed permutation. First, we calculate the total XOR of all the numbers from 1 to n, where n is the length of the original permutation. This is done using a loop that iterates from 1 to n and applies the XOR operation cumulatively. Next, we calculate the XOR of all elements at odd indices in the encoded array. This is necessary to isolate the information needed to determine the first number in the original permutation. Using these two results, the first number in the permutation is found by taking the XOR of total XOR and odd encoded XOR. Finally, we initialize an array to store the decoded permutation and set its first element to this calculated value. We then iterate through the encoded array, using the property of XOR to sequentially reconstruct the remaining numbers in the permutation. After completing the decoding process, the method returns the reconstructed permutation array. This final step ensures that the decoded permutation is available as output, which satisfies the requirements of the problem. The logic here relies heavily on the properties of XOR, which allow us to reverse the encoding process efficiently. By combining the XOR calculations in sequential decoding, we achieve an optimal solution that works in linear time, making it suitable for large input sizes. To decode the XORed permutation, we start by calculating the total XOR, which is the XOR of all numbers from 1 to n. Here, n is determined as the length of the encoded array plus 1, so n equals 5. We calculate total XOR step by step as follows. Starting with 0, we XOR it with 1, then 2, then 3, and so on up to 5. The intermediate values are 0, 1, 3, 0, 4, and finally 1. Hence, total XOR equals 1. Next, we compute the odd encoded XOR, which is the XOR of all elements at odd indices in the encoded array, using 1-based indexing. The values at these indices are 5 and 6. Starting with 0, we XOR it with 5, resulting in 5, and then XOR it with 6, resulting in 3. Thus, odd encoded XOR equals 3. Finally, we calculate the first element of the permutation using the formula first equals total XOR caret odd encoded XOR. Substituting the values, first equals 1 cubed equals 2. Now that we have the first element of the permutation, which is 2, we can decode the entire permutation using the relationship permutation, I equals permutation, I1, caret encoded, I1. We start with the permutation as 2. For the second element, we compute 2 caret 6 equals 4, so the permutation becomes 2, 4. For the third element, we compute 4 caret 5 equals 1, resulting in 2, 4, 1. For the fourth element, we compute 1 caret 4 equals 5, giving 2, 4, 1, 5. Finally, for the fifth element, we compute 5 caret 6 equals 3, resulting in the complete permutation, 2, 4, 1, 5, 3. Moving to another example, with encoded equals 3, 1, we first calculate total XOR. Here, n equals 3, so total XOR equals 0 to the power of 1 caret 2 caret 3. The intermediate values are 0, 1, 3, and finally 0. Thus, total XOR equals 0. For odd encoded XOR, we consider only the value at the 1-based odd index 1, which is 1. Starting with 0 and XORing with 1, we get odd encoded XOR equals 1. Having calculated total XOR and odd encoded XOR, we can now find the first element of the permutation using first equals total XOR caret odd encoded XOR. Substituting the values, first equals 0 to the power of 1 equals 1. To decode the full permutation, we start with permutation equals 1. For the second element, we compute 1 caret 3 equals 2, resulting in 1, 2. For the third element, we compute 2 caret 1 equals 3, giving us the complete permutation, 1, 2, 3. Now, let's consider a third example where encoded equals 1, 2, 3. Here, n equals 4, so we compute total underscore XOR equals 0 to the power of 1 caret 2 cubed caret 4. The intermediate XOR values are 0, 1, 3, 0, and finally 4, so total underscore XOR equals 4. For odd underscore encoded underscore XOR, we consider the odd indices 1 and 3, corresponding to the values 2 and 3. Starting with 0, XORing with 2 gives 2, and XORing with 3 results in 1. Thus, odd underscore encoded underscore XOR equals 1. With total underscore XOR and odd underscore encoded underscore XOR calculated, we can determine the first element of the permutation as first equals total underscore XOR caret odd underscore encoded underscore XOR. Substituting the values, first equals 4 to the power of 1 equals 5. To decode the permutation, we initialize it as 5. For the second element, we compute 5 caret 1 equals 4, resulting in 5, 4. For the third element, we compute 4 caret 2 equals 6, giving 5, 4, 6. For the fourth element, we compute 6 caret 3 equals 5, completing the permutation as 5, 4, 6, 5. This demonstrates how we can decode the original permutation from the encoded array using XOR operations and a step-by-step approach. To understand the time complexity of our solution, we need to break it into its individual steps. First, we calculate total underscore XOR by iterating through all integers from 1 to n. Since n is derived from the length of the encoded array plus 1, this step involves n iterations, with each iteration performing a constant time XOR operation. This gives us a time complexity of O(n) for this step. Next, we compute odd underscore encoded underscore XOR by iterating over the odd indices of the encoded array. Given that the encoded array has n1 elements, this step runs approximately n1/2 iterations, and again, each iteration is a constant time XOR operation. This also results in a time complexity of O(n). Finally, we calculate the value of first by performing a single XOR operation between total underscore XOR and odd underscore encoded underscore XOR. Since this is just one operation, it has a time complexity of O(1). The next step involves decoding the permutation. For this, we iterate through the entire encoded array, which has n1 elements, and compute each subsequent value in the permutation using the XOR operation. Each iteration involves a single constant time XOR operation, so this step also has a time complexity of O(n). When we sum up the contributions from all these steps O(n) for total underscore XOR, O(n) for odd underscore encoded underscore XOR, O(1) for calculating first, and O(n) for decoding the permutation, the overall time complexity of the solution becomes O(n). This linear time complexity makes the algorithm highly efficient, especially when compared to more naive approaches. Now, let's analyze the space complexity of the solution. The first thing to consider is the auxiliary variables used in the computation, such as total underscore XOR, odd underscore encoded underscore XOR, and first. These variables occupy constant space, giving us a space usage of O(1). However, we also need to account for the output array, permutation, which is constructed to store the decoded sequence. Since this array has a size of n, its space complexity is O(n). When we combine the contributions, the total space complexity of the solution is dominated by the output array, resulting in O(n). This means the algorithm is space efficient, using only linear space relative to the input size. If we compare this optimized approach to a brute force method, the efficiency becomes even more apparent. A naive approach would involve generating all possible permutations of n numbers and checking each one against the encoded array. Generating n permutations and verifying each would result in a staggering time complexity of O(n). *n, which is computationally prohibitive. Additionally, the space required to store these permutations would be O(n). In contrast, the optimized approach leverages the properties of XOR to directly compute the result without generating permutations. This reduces the time complexity to O(n) and the space complexity to O(n), making it far more practical for large inputs. Finally, let's examine the algorithm's performance under different scenarios. The great thing about this solution is its consistency, whether it's the best case, average case, or worst case. the number of iterations and operations remains directly proportional to the size of the input. This is because there are no conditional branches or paths that could cause the algorithm to deviate from its linear complexity. To solidify this, we can look at the mathematical proof. Each XOR operation is O(1), and the solution involves a fixed number of linear loops, either over the range, 1, n, or the encoded array. These linear operations dominate the computation, ensuring that the time complexity remains O(n) across all cases. Similarly, the space complexity is O(n), driven by the size of the output array. This consistency makes the algorithm robust and predictable in its performance. When working on this problem, some common mistakes can lead to incorrect solutions or inefficiencies. One frequent issue is misunderstanding the problem statement. For instance, the input array encodes specific relationships between elements, often through operations like XOR or sums. If these constraints are not fully analyzed, it can result in incorrect assumptions about the output. This is why it's crucial to take the time to understand these relationships before diving into the implementation. Another common pitfall is overlooking edge cases. For example, minimal inputs, such as when n equals 1, or maximal inputs, like when n is 100,000, can break solutions that aren't robust. Some solutions may also fail if the encoded array doesn't form a valid sequence, leading to runtime errors or unexpected results. Lastly, relying on brute force methods, such as generating all permutations, is both computationally expensive and unnecessary. This approach is infeasible for large inputs due to its factorial time complexity. Instead, focus on identifying patterns or mathematical properties that simplify the process. Another mistake to watch out for is the incorrect use of data structures. For example, using a list instead of a set for lookups can significantly increase runtime, especially for larger inputs. A set allows for O(1) lookups, whereas a list lookup could push the complexity to O(n)² in some scenarios, making the solution inefficient. It's also important to validate intermediate results as you work through the problem. Some solutions make assumptions about intermediate steps, such as decoding without verifying whether the constraints are being met. This can lead to logical errors that are hard to debug. Always ensure that intermediate results align with the problem's requirements before moving forward. Now, when tackling problems like this in an interview setting, there are a few key insights to keep in mind. First, pattern recognition is critical. Encoding and decoding problems often depend on recognizing relationships, like XOR or some properties, so it's vital to analyze the input-output mapping for these patterns. Additionally, don't hesitate to ask clarifying questions. For example, confirm with the interviewer whether the encoded array can be empty or if all elements are guaranteed to be distinct. Another tip is to optimize early. Given computational limits, such as n being up to 100,000, it's clear that a brute force solution won't scale. Instead, explore mathematical properties or efficient algorithms, such as leveraging XOR or prefix sums. If you get stuck, try solving the problem manually on a small test case. This can often reveal patterns or highlight where your logic might be going wrong. Finally, it's helpful to draw connections to related problems. For instance, problems like missing number or single number involve XOR properties and can build your understanding of similar techniques. To approach this problem effectively, consider alternative strategies that optimize for both time and space complexity. One powerful method is an optimized XOR approach. XOR is particularly useful because of its associative and commutative properties, allowing you to solve the problem in linear time. However, this does require a solid understanding of XOR's behavior to apply it correctly. Another option is using prefix sums for problems involving sums or differences. This technique reduces repeated calculations and can improve efficiency, though it may require extra space and careful handling of indices. Finally, binary search can be an effective tool for certain encoding problems, particularly when the input is sorted or exhibits monotonic properties. While binary search is highly efficient, its applicability depends on the structure of the input. By mastering these approaches, you can adapt your solution to the problem's constraints and achieve the desired optimization. Great job making it to the end. To recap, we reviewed the problem, analyzed its requirements, and solved it using efficient techniques. Remember the key takeaways about XOR properties and optimization strategies. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!